Good morning, everyone, or good afternoon, depends on where you are joining us. Welcome to the 2025 Water Talks. This is the first one from a series of Water Talks. My name is Stavros Kavouras, and I'm going to be the speaker today. Before we get into the topic, I have a couple housekeeping items. For those that are interested in continuing education points, we will be sharing a couple links in the chat so you can see where you can reach afterwards for CEUs. Depends on where you're coming from, the American College of Sports Medicine and ATA or the dietetics. So follow those links. So we'll start with the presentation, then we will have Q&A at the end. So if you have any questions, please put them in the Q&A on your side. And let me show you. This is just to get an idea, a little bit of a taste of what is coming. We have 6 talks scheduled for 2025, with the first one being the one today. And we have great speakers like Richard Johnson, which is the next one, Robert Salis, Brenda Davey, Lawrence Armstrong, and Isha Cherkudian. So we'll share with you more information in the future for registration. So today's topic is obviously about hydration, and we will be talking a little bit about how hydration impacts health and performance. Some disclosures, and the 2025 Water Talks is commercially supported by Unilever Wellbeing Collective. So thank you for supporting this talks. So did you know that hydration and fluid intake are the least studied topics in nutrition? Have you noticed that my plate doesn't have water or any other fluid by any chance? So I remember when 2011, when it first got published, for a second I got very excited when I saw the circle and I thought it was water, but very quickly I realized it's dairy, which is important, but it speaks a little bit to why many times we use the term water, the forgotten nutrient. We have forgotten to include it, and we have still to learn a lot about the importance of hydration on health and other outcomes. Do you know how much glucose you have in your blood? And to help you, this is the quick answer. We have only 5 grams of glucose in our blood, which is like roughly 20 calories. Sometimes I joke when I say if we blink our eyes quickly, we can pretty much deplete those 20 calories fairly quickly. When we wake up in the morning, we have a little bit more in our liver. We have 50 to 80 grams of glycogen stored in our liver if we're fasted, and this will be used unless we have some breakfast to refuel that amount. And even though we have relatively small amount of blood in our, a small amount of glucose in our blood, we can see that when we take a random blood sample, it can range, if you have normal blood glucose, what we call normal glucose regulation, and if you're not diabetic, any range of blood glucose anywhere between 70 to 200 milligrams per DL, it's considered normal. So what I'm trying to say, we have so little glucose in our body, but the range is really large, and we can really see many changes throughout the day, even though we only have 5 grams of glucose in our blood. On the other side, we have body water. We know that most people, at least 50% of our body is made out of water. So if you do a quick math for an average size person, you know that you have at least 40 liters of water in your body, which, if you translate that into gallons, is more than 10 gallons of water. Even though we have so much water, a small decrement in total body water, as much as 1% of dehydration, can decrease exercise performance, especially in the heat. And you typically read in a textbook that dehydration of 10 to 15% of body weight could lead to death. So this is what I like to call the hydration paradox. We have so much, but it's so important that even a small decrease in total body water can really have a negative impact on health. So most of the things we know about hydration and most of the things we have learned over the years, they're primarily coming from the exercise sphere. So what happened to our bodies when we exercise primarily in the heat? And what I'm planning to do today, actually, I'm going to take you through a journey from starting around early 1912, which is some of the first data that we have, and then I will continue to latest data that we have nowadays. So 1912, I think, was an important event happened in 1912. It was the 1912 Stockholm Olympics in the marathon event, where the Portuguese runner Francisco Lázaro was participating in the race. He was one of the best runners. And he had noticed that when he was sweating excessively, his performance was lower. So, however, he had not associated, I think, dehydration with excessive sweating. So he decided just to stop the sweating. So this is what he did. He applied a thick layer of wax or grease in his body. And as a response, his uh, body was not able to thermoregulate and dissipate heat. He collapsed at the 30 kilometer. His body temperature was over 104 degrees Fahrenheit, and he died next morning from complications of heat stroke. So a very unfortunate event, obviously, but it was one of the first lessons that when you dehydrate, you're not performing well. And if you try the alternative, which is blocking sweating, then you create a massive problem in your ability to dissipate heat, which is life-threatening. So from 1912 all the way to the 40s, there was this understanding that drinking during exercise is bad for you. And this is a quite old paper where they were trying to study, actually, the intention of that paper was to show how bad is drinking before exercise. And they even had a hypothesis. They were saying that if you drink, the distension of the stomach with large amount of water decreases the capacity for strenuous exertion. So they were trying to prove that drinking before exercise will decrease exercise performance. Obviously, they didn't find that. And they concluded that it's probably okay not to prohibit people from drinking during exercise. So even though the common sense in the 40s was that drinking during exercise is bad for you, some other scientists, and this is from the Harvard Fatigue Lab, Pete, Johnson, and Consolazio, they were studying how people regulate body temperature when they exercise in the heat, and they were trying to see human behavior on how much you drink when you had the libitum access to water. So in this study, for instance, they found one of the interesting findings. It was that drinking during exercise, it's rarely above 2/3 of net water loss. So what it means, when you drink ad libitum, when you drink based on how you feel, which is primarily how thirsty you feel, you rarely drink close to what you lose via sweating. So from the 40s all the way to 80s, there was a lot of misinformation and a lot of confusion about whether you drink or not. And I think the 80s was the beginning where many studies start coming out, really showing that dehydration can have a significant negative impact on exercise performance. This is one of the first studies by Larry Armstrong, where he took runners and he made them run 1,500 meters, 5 kilometers, and 10 kilometers in two different conditions, whether they were euhydrated, which is the blue data, or dehydrated, which is the red data. So he found that dehydration decreases exercise performance by 3 to 6%, which is the y-axis actually is running speed. So lower running speed, indicating lower performance. And if you think of 3% as being a relatively small number, 3%, it's a massive difference between being, first or not even qualify to be in the finals in any event. Like 3% could be as much as more than 100 feet behind your best yourself when you're you hydrated in an event like 1,500 meters. Also, around the same time, if an adult tried to explain the physiological mechanism that describe the decrease in exercise performance. And in this diagram, we can see that the changes in plasma volume, which is evident with dehydration, as you decrease plasma volume, your stroke volume, which is critical for proper cardiovascular function, also declines. So the lower your plasma volume, the more you dehydrate the water from your blood, the lower is your stroke volume. And as a response, your ability to produce work is significantly declined. We also do the study a few years later in 1997 at the University of Connecticut, and that was during my PhD a long time ago, where we took not specifically high-level athletes, but active individuals that they were doing a brisk walking in the treadmill in a warm environment, and we measured their core temperature under two different conditions, whether they were euhydrated, which is the white data, or -3% dehydrated. So it's easy to see that there was a statistically significant difference and quite substantial, actually. You can see at the end of exercise about 1 degree Celsius difference in internal body temperature. And that difference was evident even from the very beginning. You were standing on the treadmill with -3% dehydration. Your core temperature is higher just standing there without even doing any exercise. We also measure many things like heart rate, and we found your heart rate when you do this relatively low intensity exercise is significantly higher when somebody is dehydrated. And you can see heart rate of around 135 maybe at the end of exercise versus close to 155 to 160 beats per minute. So later on, close to 2000, there have been many papers really quantifying how dehydration impacts exercise performance. And I think one of the interesting findings of that time, it was the data that we see as far as the role of dehydration on not necessarily on endurance type, like running or cycling, etc., but in events like basketball, as far as skills related, like we see here, the decline or the amount of time that it takes you to perform skills that are very similar to the skills and the drills that you do in a basketball game, and how your accuracy declines with dehydration when you do free throws in a basketball game. So 1% dehydration, 2%, 3%, and 4% dehydration. You can see that from 2%, you have statistically significant decline in your accuracy. More data were published around that time with other sports, like even sports like golf, indicating that dehydration decreases accuracy in sports like golf as well. 2004 was an important year where the U.S. dietary guidelines was published. At the time, it was the Institute of Medicine. Now it's the National Academy of Medicine, where we got some guidelines on how much we should drink. And this is a summary table of those numbers. So for the purpose of this day and for sake of time, I would ask you to concentrate on adults, men and women, which is the dietary guidelines is 3.7 and 2.7 liters of water per day. So just to clarify, because those are dietary guidelines for water, this water refers to water molecule, not necessarily plain water or water coming only from drinks. So water is all the water that we eat and drink. So water that comes from any food, fruits, vegetables, and the water there is in pretty much in everything we eat. Um, and of course in beverages. And beverages is approximately 80% of total water intake. For most people, about 80% comes from fluids. So if we do this calculation, if we take the 2.7 liters per day for women and 3.7 per liters, and we calculate the 80%, which is what we drink, then this number becomes 2.1 and 3 liters per day. If we want to translate this 2 liters and 3 liters into glasses per day, this is approximately 8 glasses per day and 12 glasses per day of those tiny small glasses, at least for the United States, that most of us, we don't have anymore in our home, since most of the glasses that most people drink, I would say, they're much larger than this. But a glass or a cup of water, that would say, or a little bit less than 240 ml per glass is roughly 8 to 12 glasses. So for females is around 8 glasses, for males is about 12 glasses. So there has been a lot of controversy about whether this is good for everybody, and how about if I'm a small person, or how about if I'm a massive, I don't know, football player, 400-pound. And just as a reminder, like for every dietary guidelines that we give, those are dietary guidelines for population level. So it's not necessarily guidelines for every single person, that whether you're physically active or inactive, whether you live in Alaska or whether you live in Greece. So this is a population level general dietary guidelines for the United States. So moving on in the timeline, in 2010 was the year where really we learned much more about the how and the mechanisms about how dehydration impacts exercise performance. One big question that came up, it was whether drinking to thirst is the best way to optimize performance. And I can reveal the answer right from the bat, that drinking to thirst is not the best way to hydrate. It's not the best, especially if you're thinking for optimal performance. So we did a study that was published in 2017. We took high-level cyclists, we made them complete almost like a race protocol in a laboratory setting, and we found that drinking by following a prescribed protocol, what we call individualized hydration protocol, based on how much you sweat and how much your body needs, it led to a better cycling performance compared to people drinking ad libitum on their own, how they felt like drinking, like the way that people drink when they ride their bikes on their own. Also, the similar timeline, we found we saw a lot of data on how mild dehydration, and we define mild dehydration as less than 2% of dehydration, less than 2% dehydration, and the impact of this mild dehydration on exercise performance. These are a couple studies that we did, one in a laboratory setting and another one in an outdoor setting. And again, we found that even mild degree of dehydration, something like 1% of body weight dehydration, also impairs cycling performance. We also try to answer another question. This is something that quite often comes up in the hydration literature field, which is dehydration a real thing, or is it something that subjects that participate in studies develop as what we call anticipatory bias? So just to describe a little bit what I'm trying to say is that if I bring a subject in the lab and I tell them that today you're going to be doing the dehydration trial, you're not going to be drinking, then the subject is already disposed, is expecting to do worse. So the question that comes up, is it really physiology that your body cannot perform, or is it psychology that you have prepare your body to do worse? You feel that you should do worse. That's why you do lower exercise performance. So this is the protocol that we did. We thought about it extensively. So we try, first of all, to hide whether you're drinking or not, which is quite difficult. So we use a nasal gastric tube. We pump fluids directly into their stomach in one of the trials, and we make people uh, uh, either euhydrated or dehydrated based on pumping a lot or very little fluids. And we also make people to drink a very small amount of water, like 25 ml of water every 5 minutes, just to decrease their thirst and not being thirsty, because being thirsty, it creates a lot of negative feelings. And many people argue that this uncomfortable situation of being thirsty and feeling miserable is what decreases exercise performance. So we found that dehydration does impair cycling performance, whether you're thirsty or not, and especially when you do what we call a blinded setup, where people are blinded, they don't know whether they're dehydrated or not, and whether they're thirsty or not. And similar data have been published actually from other scientists from Lapham University. The group of Lewis James have shown similar data actually in multiple studies that this is the case. Moving on, in 2012 actually was, I would say, a landmark of a significant increase on scientific interest between how hydration impacts health, which is probably what affects what I like to say the other 90 something percent of the human population, that they're not Tour de France cyclists, they're not running marathons, they're not professional athletes, etc. So the question, some of the first questions that we try to answer in the literature is, how much water people really drink, like as an observation, how much fluids people drink. So this is some data that I have selected for specifically for older adults, where the data actually do not look that good. If you pay attention, you will see that 64% of women and 96% of men, almost all men, do not meet the dietary guidelines. And if you look carefully of what this data show, they show that women were minus 2.5 cups of water per day and 5 cups of water per day for men. The average value was below the dietary guidelines for older adults. And those were data from the National Health and Nutrition Examination Survey, the 2005 and to 2010 cohort. So they took a 5-year period from the National Nutrition Survey, and they analyzed this data. So also, again, the group of Adam Jornowski analyze again the enhanced data for children, the 4 to 13 years old children from the United States. And here in this bar diagram, you can see different age groups, 4 to 8 years old, boys and girls, girls 9 to 13, boys 9 to 13, and you can see that this red part of the graph represents the mean deficit compared to the dietary guidelines of water intake. The small pie charts indicate the percent of children that fail to meet the DRIs for water. 75%, 83%, 85% of children do not meet the dietary recommendations for water. Also from another enhanced analysis, again from the National Health and Nutrition Examination Survey, they look at hydration now, looking at urine biomarkers from the 2009-2012 cohort, and they found that more than 50% of children that were underhydrated described based on urine osmolality greater than 800 milliosmol per kilogram of water in urine. One interesting observation was in 1 out of every 4 children, 25% of children did not consume plain water. So the water that they take throughout the day either comes from solid food or from other beverages like juices, milk, or any other drinks, but not from plain water. So to try to dig into this observations and trying to give an answer why people drink relatively or at least in some groups, a significant percent of population consume small amount of water, I need to explain a little bit on the physiology of how we regulate body fluids. So we drink when we're thirsty, or we tend to say that we only drink when we're thirsty, which probably not necessarily true. Sometimes we drink just because we want to drink, or we have water in front of us, or you listen to my talk. Probably if you listen to me, you will be drinking probably more, whether you're thirsty or not. But anyway, so let's see how thirst is regulated. So thirst is stimulated by 2 receptors. So one is the osmoreceptors here on your left, and the pressure receptors, also known as baroreceptors on the right-hand side. So both of them are the ones that they really stimulate. When they get activated, they stimulate thirst. And actually, the osmoreceptors are the ones that are particularly sensitive and are the first line, I would say, of response for thirst. When the osmoreceptors are activated, other than getting thirsty, you also have stimulation of arginine vasopressin, also known as antidiuretic hormone. And this hormone is stimulated primarily from the osmoreceptors, but it's also stimulated by the baroreceptors. And I have intentionally larger arrow here on the left because the osmoreceptors have a stronger effect, at least within the physiological range of vasopressin regulation. So the effect of increase in vasopressin in our body, in our blood, is we have a decrease of urinary output. So we pee less, and when we pee, the urine is way more concentrated. The baroreceptors, other than stimulating vasopressin, they also stimulate aldosterone through a mechanism in the kidney. And as a response, we decrease urinary sodium loss. So your body, when aldosterone goes up, your body's trying to spare sodium and keep extra sodium in the body because sodium can help in holding water. So both of those responses, what they do, they prevent of excessive sodium loss and water loss through urination. So this way your body can hold extra water. So trying to answer the question why people do not drink enough, I will have to show you a little bit of some of those data on how vasopressin is regulated. So here in this diagram, we have vasopressin on the y-axis, and we have osmolality, which, as I mentioned earlier, is the main signal to produce vasopressin. So as osmolality goes up, we have a strong linear relationship of vasopressin. So higher osmolality, which is a response to dehydration, we have a higher plasma vasopressin. In a similar fashion, osmolality also stimulates thirst. So higher osmolality, we also have higher thirst perception. If we superimpose both of those diagrams, we will see that there is a delay, or vasopressin is the first response as soon as plasma osmolality starts going up. And then thirst doesn't get stimulated until vasopressin is already significantly higher. So why this thing happen? Why we do have this delay between secretion of vasopressin versus thirst stimulation? I think this is a beneficial and substantial survival skill or survival tool that our body has. And if we compare ourselves, for example, from the study, humans here on the top versus chimpanzees on the lower part, this complicated diagram, what it shows is what is called water turnover, how your body handles water and how much water you need to consume throughout the day, whether you're a sedentary or hunter-gatherer. And they have collected data in people like that in Africa and in chimpanzees, whether they live in a zoo or in the wild. And they found that humans need about 3 to 4 liters per day versus chimpanzees need almost the double amount to be able to survive. So I think that by itself can explain why humans can survive pretty much everywhere in the planet versus chimpanzees cannot survive in places like where I live in Phoenix, for instance, in the middle of the desert. So water drinking is what psychologists call a motivated behavior. And it's able to weigh the need for water against competing survival demands like need for food, need to hunt an animal and go after, a deer, be able to kill the deer so you can feed the family or cultivate the earth under heat conditions, even if you don't have water. So the question that you probably think of now is like, okay, humans are designed to survive with less water than other mammals, but what happens when you're not drinking adequate amount of fluid? So this is a very interesting study. When it was published in 2012, was one what I call one of the classic studies where they took 250 people and they select specifically 100 subjects that they were either the 50 high drinkers, the one that they consume on their own, they tend to consume a lot of water, what we call in the literature high drinkers, versus the low drinkers, the ones that they tend to drink small amount of water. So out of the 250, they selected the 50 that they were drinking the most amount of water and the 50 that they were drinking the lowest amount of water. So what they found is that those two groups, the high versus the low drinkers, their main difference, it was that the low drinkers had significantly higher arginine vasopressin or antidiuretic hormone. Interestingly, cortisol was also higher in the group of low drinkers, which unfortunately I don't have time to describe much about what happened and why the cortisol seems to be chronically elevated in low drinkers with high arginine vasopressin. So if many people are not drinking adequate amount of water, are people dehydrated? And the answer is maybe some people. So athletes might be dehydrated, and especially transiently when they do high intensity exercise in the heat, when they train in warm environments, they tend to dehydrate during practice and then rehydrate afterwards. Some of the older adults, because we know older adults have suppressed thirst, that's why they're not drinking adequate amount of water. Manual workers, I live in Phoenix. Like today, for instance, the temperature is going to reach close to 47 degrees Celsius, if that tells you something, which is about 117, I believe, degrees Fahrenheit. So if you work outdoors, being a roofman or doing construction work in these temperatures, I guess you probably cannot drink enough to avoid dehydration during work hours. And also some medication, and here I have a couple of medications that we know have negative impact on thirst and fluid intake, like the selective serotonin reuptake inhibitors like Prozac or antidepressant medication, and the beloved Ozempic and its family, the GLP-1 receptor agonist, that they seem to lower thirst. So what I'm trying to say, this categories, I guess, might be higher risk on being dehydrated, either transiently or chronically dehydrated. But most people, I think, they're not dehydrated. but they're not optimally hydrated. And I like to use the term underhydrated. So let me describe a little bit what is underhydration versus dehydration. So when somebody is consuming small amount of water, does not automatically create a water deficit. And dehydration, by definition, means that you do have a significant water deficit. So in the spectrum that you can see here, you have the green zone, which is the zone of euhydration. And throughout the day, we want to be, or we want to be as much as possible within the level of euhydration where we have optimal amount of fluid intake and we're well hydrated. However, throughout the day, we might dip a little bit lower because we went somewhere, we forgot to bring water, or we're busy, we don't drink, or we're maybe exercise outside, etc. And also some other times we might drink a little bit more than our body needs and we dip into the area of overhydration. And obviously, if you lose significant amount of water, then you can dip into the dehydration level. If somebody is a low drinker, tends to live within this zone of underhydration, where, to be quite honest, total body water probably doesn't change enough or measurable enough to really be able to assess it and have a significant measurable impact. However, your body stimulates the fluid regulatory hormone, so you have higher vasopressin to be able to decrease urinary output and keep your body water as well as possible. Obviously, if you are in this level of underhydration, you're definitely higher risk of dipping into dehydration throughout the day. If you have a challenge like do anything outdoors or practice or do chores in your garden, etc. So you might be higher risk of developing dehydration. So I tried to describe this condition of underhydration a few years ago in this editorial. And if you pay attention in this cycle, underhydration is described of low water intake, total body water, it's probably not significantly altered. It's a state where you're not really thirsty, because if you were thirsty, you will be drinking more. Plasma osmolality or plasma sodium is within the normal range. And the only thing that we see different is vasopressin is higher. And as a response, urine osmolality is also elevated, and you produce less and more concentrated urine. So the next question is underhydration bad for health? And the quick answer is yes. So we have a lot of preliminary evidence from associative or epidemiological studies. Like this is a study from an Australian cohort showing that fluid intake or low fluid intake is a risk for chronic kidney disease. So if you look here, they took a cohort and they split it in 5 categories from low fluid intake. And you can see here the median intake all the way up to high fluid intake, close to 3 liters or fairly close to what is the dietary guidelines for adult males. And they found the higher the level, the lower the risk of chronic kidney disease. We also did a study looking at patients with recurrent kidney stones. So this particular populations, those were all patients with recurrent kidney stones. We measure their crystallization risk, and we also measure their urine osmolality, trying to show whether urine osmolality is associated with the risk of crystallizing new kidney stones. And we found a very strong and significant relationship. And we also identified threshold values of urine osmolality, which was around 500 for women and 577 for men, indicating that if urine osmolality is higher than these values, then you're high risk of developing or crystallizing new kidney stones in your nephrons. So definitely drinking less and having more concentrated urine, it's a risk for reproducing kidney stones. The kidney evidence actually have been around for several years. So we have, I would say, strong data on kidneys with intervention studies and randomized controlled trials. But what is interesting, and we have less data, is something relatively new, which is the impact of fluid intake on glucose regulation. These are some data from a French cohort where they study almost 4,000 adult men and women. They follow them for 9 years, and they found that low water intake was inversely and independently associated with the risk of developing hyperglycemia. So drinking less water, it was associated with higher risk of developing hyperglycemia, high blood glucose. From another cohort from Sweden, Ola Melander and his colleagues showed that plasma copeptin, which is a surrogate marker for vasopressin, is a risk for developing diabetes. And they also developed cutoff points of roughly 6.1 for women and 10.7 for men, that when copeptin is above those levels, then you have a risk 3 to 4 times higher for developing diabetes, which is an equally strong risk if you compare, for example, the risk of obesity for development of diabetes. So if you look back in this diagram that I had earlier, as far as the osmotic threshold for vasopressin and for thirst, and you look when you're in this zone, the zone that you have stimulated vasopressin, but you're not thirsty yet. This is the zone of underhydration. And you can see plasma vasopressin, which is around from, I would say, 3 to 11, 12 picograms per ml of vasopressin, which is fairly similar to these values of high risk of developing diabetes. So some interesting data that we have from experimental animals are presented in the slide. So what they did in this study, they took mice and they inject them for 4 weeks with vasopressin, daily injections of vasopressin. And they found that within 2 weeks, the animals, which is the animals that were injected with vasopressin, which is the dark blue data, had increase in fasted glycemia. So they had higher fasted blood glucose compared to the control, which is the middle bar, or compared to the white data, which is mice that they were fed with higher amount of water, that were immersed the food in water and made them drinking more water per day. So they also took, so they concluded that high vasopressin could induce diabetes, and higher water intake was associated with lower fasting plasma glucose. They also took Zucker obese diabetic rats, and they treat them with the blocker of vasopressin, the V1 AVP receptor blocker, so drugs that block vasopressin. And they found that by blocking the effect of vasopressin, the blood response following injection of glucose was significantly lower after using the vasopressin blocker compared to the control. So in my lab, we did a study, a clinical trial with 60 subjects where we brought them in the lab and we artificially forced them to increase vasopressin by doing intravenous infusion of hypertonic saline. And after the 2 hours of hypertonic saline infusion, we gave them 75 grams of glucose, and we observed the responses on their insulin and glucose. And we found that plasma glucose was statistically significantly higher during the 4 hours oral glucose tolerance test. And that was associated with higher levels of glucagon and lower levels of insulin during the OGTT test. we are obviously very interested in this situation or this condition of underhydration. And Jody Stuckey and myself and some other colleagues, we analyzed the data from Enhance again, and we look at association between underhydration and obesity, chronic disease, and even death. And we found that underhydration is associated with obesity, chronic disease, and even death within 3 to 6 years in the United States in population of 51 to 70-year-old adults. The last few years, there is a series of publications that I would like to present here from the Natalia Dimitrieva's group from NIH, from the National Institute of Health, the National Heart, Lung, and Blood Institute in Bethesda, Maryland, where they're using this specific methodology. They're taking existing data and they're looking at normal plasma glucose, but they're splitting the data within a range of plasma, I'm sorry, not glucose, I meant they're looking at plasma sodium within normal range between 135 to 145, but they're looking particularly at people with plasma sodium over 142, which is still normal, but higher level within the normal range. So what they found that if you take that group with slightly higher than 142 millimole per liter plasma sodium, which is an indication of underhydration, you have a higher risk for many chronic disease. And this suboptimal hydration state, it promotes degenerative disease. So they predicted, if you look here in this part of the diagram, that optimal hydration could decrease the disease prevention in a group of 70 to 85 years old by 48% for dementia, 24% for heart failure. And you can see other chronic disease like lung disease, kidney disease, diabetes, hypertension, stroke, etc., in a US population, which is quite impressive. Based on the same methodology, using the plasma sodium above 142, they also found that lower water intake resulting in higher plasma sodium is a risk factor for accelerated biological aging, chronic disease, and premature mortality. And they also presented data a couple years ago on the impact of suboptimal hydration on heart failure. So to summarize, I think what we know right now, it seems that underhydration, it seems to be a significant health risk, and it seems to be associated with kidney disease, cardiovascular disease, diabetes. And we also have a lot of interest in cases like dementia, longevity, and even things like mood, cognitive performance, and even social behavior seems to be affected by low water intake and underhydration. And remember, this is a condition where you're probably not dehydrated per se, but you're in a situation where you're probably not even thirsty. You're not consuming adequate amount of water. And probably the only indication that you have is that your urine looks more like the one to the right than the one to the left. You have little and concentrated urine. So I would like to close my presentation by giving you a hydration tip on what you can do to, if you want to check on your own without taking blood samples or collecting urine, etc., if you want to see whether you're drinking enough or not. So we did this study where we published a couple years ago, where we took kids and adults, and we found that if you can combine and have a UP at least 7 times per day, and if your urine is lighter in this color scale, 3 or lighter, and if you pee at least 7 times per day, then you're almost certain that you're well hydrated. So we did this analysis also for children. For children, the number of voids is a little bit smaller. It's 5 per day. And again, 5 per day with combination of relatively light color of urine, what we call straw color or lighter. So peeing for adults, I would say 7 times per day, it's every 2 to 3 hours. And having dilute urine, this is a clear indication that you're optimally hydrated. So before I open for question, I would like to thank the Hydration Science Lab group that they do all this amazing work so I can present their data, the data that they collect pretty much every day. And thank the College of Health Solution at Arizona State University for all the help in supporting this water talks. So let's close with a thought. What if improving hydration, other than all these things that we see in the literature right now, outside of improving health by hydrating better, how about if it is a gateway for a healthier overall life and well-being? Here are some suggested reading if you want to follow up and get some more information on the topic. And I'll stop right here. So let me see. Holly, would you like to, do you have, I see that we have several questions in the Q&A.
If you have any questions, you can put them in the Q&A at the bottom of the screen. The first question that we have is coffee considered a valid liquid for hydration?
Yeah, this is, I probably intentionally didn't say anything about coffee because it's probably one of the most widely asked questions that I get. So many years ago, we used to say that coffee and caffeine per se, whether it is from coffee or tea, um, can dehydrate you, which is not the case unless you reach a really high levels of caffeine intake. So moderate coffee intake doesn't cause dehydration. So it doesn't lead to excessive urinary output. So up to, I would say, an amount of up to 400 milligram of caffeine per day, it seems not to be an issue. So yes, you can count if you have 2 or 3 cups per day, taking into consideration that a strong cup of coffee, it's about 100 milligrams, then it should count towards your daily water intake.
The second question that we have are the dietary guidelines for fluid intake based on studies on the general population, or is it mostly derived from studies on athletes?
The dietary guidelines are developed from regular people, not necessarily athletes. The National Health and Nutrition Examination survey that they use to develop this type of guidelines are the beauty of this data is that it's a very large cohort, so there are thousands of people, and it's a representative sample across the country, across the United States, taking into consideration ethnic differences, age, gender, size, etc. So, but again, it's recommendations at the population level.
Next question. I've heard that you shouldn't drink above a few sips 2 hours before going to sleep because the urge to urinate can wake you up earlier and decrease your sleep quality. What do you think of that?
Yeah, this is a great point. So I would not recommend have a massive fluid intake right before you go to bed. If you drink a lot and you lay down, then you will probably disturb your sleep. So it's if and the truth is people age, especially males, and naturally prostate gland enlarges and the capacity of the urinary bladder decreases, then the urge is higher. So I would recommend not to have massive amount of fluid right before you go to bed. So trying to manage to drink more fluids earlier on in the day and try to stop as you get closer before you go to bed.
Next question, does drinking more water than needed lead to faster water loss, as the fluctuations in the colored chart you showed indicated?
So, so it depends on your hydration state. So just to give you an idea, when I mentioned that how many times you pee per day, it's an indication of how hydrated you are. For instance, if you drink above and beyond or what your body needs, you will be urinating most of it. So if you're going to the bathroom every 15 minutes, you're overdoing it. So you have to slow down. So drink a massive load. If you're dehydrated and you drink a lot of water, your body will try to hold most of it. But no matter how hydrated you are, your body will always excrete a portion of what you're drinking.
Next question, how long does it typically take for AVP to act in order to rebalance the body water compartments?
AVP AVP has a short half-life and it can change quickly. So and vasopressin actually AVP changes even before you start absorbing the fluid. So there are studies that have been done with that they have used nasal gastric tubes and they were extracting the fluids that you were drinking. So just the act of swallowing suppresses vasopressin. So what I'm trying to say is that the response, the vasopressin response is very quick. So when you have high vasopressin and you start drinking, vasopressin goes down fairly quickly.
Next question, how the use of sports drinks with salt or salty diet could affect the pee frequency, especially for adults?
Yeah, when you consume something with electrolytes, your body tends to hold them a little bit better versus if you drink just plain water. So if you're in a, for example, if you are in a dehydrated state, you have a long workout and you rehydrate with an electrolyte solution, then you have faster and more effective rehydration, at least in the acute phase, in the first acute phase.
Next question, can the EGFR number improve after consistent hydration?
Um, so the GFR is an indication of kidney function. So improving hydration, it has a positive long-term effect in the kidney function. So yes, you can. Of course, in some cases, if you have, I don't know, uh, chronic kidney disease, like a high level of chronic kidney disease, third, fourth stage, etc., then it's very difficult to reverse if this is, I'm not sure if this is the question, I guess.
What do you think of the idea that drinking too much water can flush out electrolytes from the body?
So it does. So when you drink too much water, you do. So let me start over. So when you consume small amount of water, your ability to excrete excess sodium is decreased. So being better hydrated and drinking more water, it gives you the ability to excrete extra sodium. And if you think people that are sodium sensitive and having sodium sensitive hypertension, consuming extra water can help them regulate better sodium levels and blood pressure, even though most people, I would say, most people are not sodium sensitive. So it depends on the population. The percent of sodium sensitive hypertension, it could be from as low as 15%, and in some population, much higher. So drinking excessive amount of water and going to the bathroom, I don't know, every 30 minutes, then it can lead to a higher urinary sodium excretion and other electrolytes.
Do you have time for 6 more questions?
Uh, let's take a couple more.
Okay. For the dehydration data in the charts presented from 2005 to 2012, is there data available that is from the last 1 to 2 years?
Um, I'm, I'm sorry, can you repeat the question? I'm not
For
sure.
the dehydration data, the charts presented from 2005 to 2012, is there data available that is from the last 1 to 2 years?
No, we don't have more recent data, but I'm aware that there is a group that is working on analyzing this data and trying to find trends throughout, from older data from ENHANCE up to very recent data.
Is superior mineral attributes in water, like flat mineral water with higher magnesium content, better for hydration if the water itself also maintains a natural molecular structure similar to that occurring in plasma?
I'm not familiar. I know there is an interest in structure water and molecular structure of water, but I'm not familiar with the literature in this area. I don't think there is evidence that changing the structure could have an impact on hydration. As far as magnesium content, etc., there is very, very little evidence that magnesium plays a significant role on hydration per se, at least in acute dehydration, rehydration studies. I saw there is a question on whether the video will be available afterwards, and the answer is yes. We can take one more question.
Okay. The excessive use of electrolyte beverages could lead to have less voids to conserve water into the body. Would this affect the number of voids and give a bad indication of hydration? Could someone be hydrated only with water and voids excessively being dehydrated?
This is a good question, and acutely you could have, so if what you drink, whether it is a high electrolyte solution versus plain water, could have an acute impact on how often you hydrate, on how often you urinate. But in a 24-hour period, and this is what we're looking into, your body can balance out. So if you have, for example, extra sodium, your body will suppress aldosterone, will excrete the extra sodium, and will balance it out. If you're going with plain water, for instance, and plasma sodium goes down a little bit, aldosterone can increase and increase the reabsorption of sodium from the kidney. So there is a mechanism to regulate that. So overall, I'm suspecting it's going to be okay. We haven't done studies to look specifically people hydrating only water, people hydrating only with electrolyte drinks, and validate whether that cutoff point that I suggested, the 7 times of dilute urine, means optimal hydration or not. So on the screen, I have the link if you want to register for the next water talk, which is scheduled at the same time for July the 23rd. And I also wanted to share with you that we have also another talk at the College of Health Solutions here in Arizona State University, which you might be interested. Too hot to handle extreme heat and drug-related risks on July the 31st. You can register in asuhealthtalks.com. Thank you very much. Holly, I think you have shared the links for the CEUs, correct?
Yes, if you want CEUs, please take the assessment and the evaluation for the governing body that you want CEUs from, and you should receive a certificate in email if you pass with 70%, and you can take that assessment as many times as necessary.
Thank you very much. Thank you for participating. Have a good day.